What do you know? Is it possible? The entirety of the host CPU task can and will be moved to the PMC FPGA module. Let's see how. Adding a processor to an FPGA device permits the implementation and execution of logic that would otherwise be performed on a host CPU. This means actually having an operating system execute on top of an FPGA and the writing and executing of real programs written in your favorite high-level language, be it C, BASIC, C++, and on. There are two approaches to obtaining the processor capability on an FPGA. The first is the soft core approach. The second is a hardcore approach. There are many soft core processors available. From Xilinx, there is the Microblaze and the PicoBlaze cores. From Altera, there is the Nios 2. And from third parties, there are, for instance, the ARM Cortex and the Freescale Coldfire, to name a few. The pros of the soft core approach include flexibility in the integration of the high-level language interface and the support required of the FPGA at the hardware level, and the tight integration of the high-level language and operating system peripheral support with the FPGA code for efficiency and streamlining of logic. The cons of the soft core approach, on the other hand, include the fact that the design of the interfaces between the two computational vehicles, the FPGA and the high-level language writing on top of the soft-core processor, can be complex, or as simple as the system architect might prescribe. Execution of high-level logic on top of an operating system will be slower than any direct FPGA implementation. And just the presence of the soft-core processor will greatly reduce available FPGA real estate for logic and DSP VHDL logic. The logic cell count of the FPGA must be chosen to adequately support the application. The most powerful approach, the hardcore processor. This is an embedded physical IC within the actual FPGA chip. For the Xilinx Virtex 5 family, Acromag has released the PMC VFX70, which includes a hardcore PowerPC 440 CPU. There are pros and cons to every approach, no exception for the hardcore approach. For the hardcore PowerPC, the pros include some minimization of the integration issues since the PowerPC is built in, and Xilinx, or the supplier of the integrated FPGA with the hardcore processor of choice, will have provided an integrated device with associated development environment. Since integration is minimized, development can move to the next phase of application development directly. The hardcore PowerPC is dedicated, fast, and occupies no FPGA real estate. And the FPGA module supplier will have provided the customer with the tools to properly manage and load both the FPGA device and the integral PowerPC. The cons of the hardcore PowerPC include the fact that the PowerPC is always there, used or not used. The hardcore PowerPC is a single CPU entity. Additional soft-core PC cores can be used to augment the capability if needed. Some level of integration over and beyond that of just loading the FPGA device is a requirement, i.e. loading of the FPGA, allocating memory, and loading of the PowerPC instruction space. Adding a processor to the FPGA is a complex extension of the basic FPGA module. Earlier, we talked about the architecture of the FPGA module, the interfaces to the memory, dual-ported SRAM and DDR DRAM, the I/O, the host computer over the PCI or PCIe bus, flash for FPGA logic storage, and the general functioning of the FPGA for the execution of logic. These are unchanged. The coexistence and work sharing between the FPGA and the PowerPC within the FPGA chip itself becomes the challenge, and it is the work breakdown where the benefits of having both architectures are accentuated. The PowerPC will add to the capabilities of the FPGA module the convenience of executing the real-time operating system of choice and providing for tight cohesion with the high-speed logic execution of the FPGA. An understanding of where the strengths of the FPGA and the PowerPC excel follows. We've got a super powerful FPGA module in hand. We've got a PowerPC on board the FPGA module. How or what is the best way to take advantage of both of these environments? We've talked about the high performance characteristics of the FPGA. As in all systems, not all tasks are high performance. Less time critical tasks can easily be relegated to an application running on a host CPU or on top of a real-time operating system executing a higher level language right on board the FPGA module itself. The dichotomy is performance versus convenience. The balance is up to the system architect. Traditionally, performance tasks would be implemented in VHDL and would include such operations as SerDes, your serialization, deserialization, protocol conversions, math library implementations, and hardware interfaces, real hardware interfaces where performance is a key. These types of devices might include UARTs, display drivers, DMA controllers, memory drivers, high-speed FIFO management. On the other hand, the more convenience-oriented tasks would be implemented in the high-level language of choice and would include such operations as algorithm execution invocation. Perhaps there you'll have such things as floating point and fast Fourier transforms, matrix manipulations, MATLAB, man-machine interfaces, data display preparation, keyboard, mouse, data transfer management. Data transfer management may be such things as file creation, deletion, opening, closing, reading, and writing. All of this is possible on a single PowerPC endowed commercial off-the-shelf FPGA module. Here it is, the Acromag PMC VFX70. This module features a Vertex 5 FPGA running at up to 550 megahertz, 70,000 logic cells, 12 DCMs, FPGA module load over the PCIe bus or from flash memory, expandable program storage, conduction cooling, flexible and adaptable mezzanine I/O, commercial and industrial temperature ranges, and the powerful PowerPC 440 built in. Thank you very much for having participated today. If you should have any questions, please feel free to contact either myself or any of us at Acromag.